Hi, everyone. Thanks so much for coming to this very early morning presentation. Today, I'm going to give a talk entitled The Problems and Promise of WebAssembly. I'm Natalie Silvanovich. I'm on Project Zero at Google, and you might remember me from previous presentations about JavaScript. Well, I've been taking a bit of a break from JavaScript and looking at the other features of the browser. And one thing I looked at that I thought was really interesting was WebAssembly. So today I'm going to share with you a bit of what I learned about WebAssembly and the sort of bugs I found. So what is WebAssembly? Well, it's a format for writing assembly code for the web. Basically, if you have JavaScript and you have something that is really mathy in that JavaScript, you can abstract that out and put it into WebAssembly, and it'll run in an interpreter or a JIT that is typically much faster than JavaScript because it doesn't do things like type checking and that sort of thing because it has more limited features. It was motivated by two reasons. One was a need for greater efficiency in the browser, and the other was a need for greater safety. Some people hope that WebAssembly will become a good alternative to running a native application on your desktop. There's a few ways you can write code in WebAssembly. One is that there's a WebAssembly assembler, so you can just write instruction by instruction and then assemble it. But the main way it's meant to be used is by writing native code and compiling it. There's some limitations to compilability, though it's getting better every day. C and C++ compile pretty well, and so do some other languages, and then some like Java, which have garbage collection, are quite far away from being able to compile well in WebAssembly. But the long-term goal for WebAssembly is to be able to basically compile any code written in any language to run on the web. It's a WC3 standard, and I'd actually say it's quite an ambitious standard. Not only do they want to make the web, safer and faster, they also want to compile every language, but people are also thinking about applications off of the web. To give one example of this, they're thinking of moving the Ethereum interpreter to WebAssembly. And that's just one example of the sort of applications that WebAssembly could have in the future. So when you think about something like WebAssembly, a language that is written to implement stuff on the web, there's kind of two possible problems. One is that WebAssembly engines aren't implemented securely, that a malicious developer can write WebAssembly that violates the security properties of the browser and can compromise the browser. And then there's a second problem where WebAssembly itself, the WebAssembly application, isn't written securely, and that application can be compromised. I'm talking about this problem today, the first one, and I'm not talking about the second one. There's actually a talk today at 12:10 about the second issue, which I'd recommend you attend if you're interested in learning how to write actual WebAssembly securely. So to start off, from a technical perspective, what is WebAssembly? Well, it's a binary format, and since right now it mostly gets loaded in JavaScript, you create a binary, and there's a keyword fetch you can use to put it into an array buffer or a typed array in JavaScript, or you can just put it in byte by byte like I did here. And what does this format actually look like? Well, like all good binary formats, it starts with a magic number and a version. And then there's a series of sections that have an ID, and depending on what the ID is, that determines what the payload of the section does. And there's actually tons of rules for these sections. They have to be in a certain order, some of them are mandatory, some of them can't have duplicates, that sort of thing. And what do all these sections do? Well, they contain basically everything you need to execute this code. So there's type information, there's imports, there's memory, there's code, there's that sort of thing. And I'll go through what each of these do in much more detail later. And then how does this format actually get parsed? Well, your first step is you have this typed array or array buffer, which is the variable wasm here. And then you create what's called a WebAssembly module. And this is the thing that parses your binary and loads it into memory. And at this point, there already started to be a few bugs. So this is a vulnerability I found in WebKit, and this is an ordering problem. So as I said, some sections are mandatory, some of them have to be in certain orders, and there's also something called a custom section, which pretty much means that if The WebAssembly engine doesn't know the ID of your section. It'll just skip over it and assume it's something it doesn't support yet. And every engine has a way that it validates these sections are in the right order, taking into account custom sections, but the WebKit one was defective. So in this case, you'll notice if there was a custom section, it just returns true, which means that you're ordering resets every time you have a custom section, and you could do out-of-order sections and violate all the rules. And there's lots of reasons why this could cause problems, but I think the most interesting one, and the one that ended up being exploited, is that there are some sections that there's supposed to only be one of, but if you could put more than one of them in, then it would start putting things into a vector past the bounds of the vector, and it turned out to be a buffer overflow. So here's another issue that turned up just in the parsing of this format. This is an issue that was in V8, and this is an integer overflow issue, and it only works on a 32-bit platform. So basically, there's one of the things that is in this format is the number of locals that each function has. And if you had a very large number of locals in V8, it would just overflow the allocation, and then or overflow the integer of the allocation, and then you would have a very small piece of memory with a very large array copied into it. So here's another issue that happens once again, just in parsing. This is in WebKit. And this is kind of a silly issue in that it's clearly just a developer error, not any misunderstanding of the specification. So in JavaScript, when you have an array buffer, you can create a typed array buffer around it. And this is basically just a view into that buffer. So for example, the variable view, that is at offset 700 of this array buffer. So if you accessed sub 0 of that view, you would get sub 700 of the variable b2. But the error they made in developing this was that they accidentally added this offset in twice. They called a function that gets the array buffer with the offset, and they forgot that it did that, and they added the offset again. So this is kind of an interesting bug, just because also it prevented this from working. It meant that if you ever had a typed array with an offset that wasn't 0, WebAssembly would just never work. So this is a bug that was probably not long for this world, but it did show up. And actually, there was sort of a similar bug in V8 that came up at the Ponies last night, which was found by Guangdong. And it's another issue where they didn't quite get the JavaScript properties of the typed array, and you were actually able to change the typed array in the middle of execution, which caused problems. So there's actually been quite a few issues in WebAssembly just with what I'd call JavaScript bindings, making sure the JavaScript properties of the objects that get WebAssembly started work correctly. So what happens now that you've got this binary format loaded into the module? Well, now you actually have to run it, and you need certain properties to run it. So you do this using an instance. So what does this instance object actually do? Well, it starts off by doing imports, and then it initializes the imports, and then it creates the exports. So there's actually more than 3 import types, but I think there's 3 that are actually interesting. There are functions, so you can import JavaScript or WebAssembly functions into WebAssembly, and then you can call them from WebAssembly. You can also import memory. Fundamentally, WebAssembly is a set of instructions like loads and stores, and they need memory they can access. And you need to import the single memory page that it uses before you run WebAssembly. And there's also a function table object, which is literally just a table of functions. And this is used to implement things like vtables, where you need the ability to dynamically call a function. So here's some WebAssembly terminology you can totally use to impress all your WebAssembly friends. So there's these 2 imports, the memory and the table. And of course, you can have many instances of the same module or different modules in WebAssembly. So if 2 instances or more instances have the same memory and the same table, they are called in the same compartment. Now, a question you might have is, well, can an instance share the memory but not the table, or share the table but not the memory? And the answer is sure. You can totally have WebAssembly that's in like half of the same compartment, but there's no reason you would ever practically do this in writing WebAssembly, and no compiler will ever generate this code. But, you know, if you want to do it to reach a vulnerability, it's totally an option. So let's talk a bit more about this memory. It's a memory page for the WebAssembly code. And right now, WebAssembly is limited to a single memory page that load and store instructions can access. And the way this gets allocated is you allocate this memory object, and it has an initial size and a maximum size in pages, and then you call grow to increase the size. And this memory then just becomes available to all the instructions in WebAssembly. And at this point, there's also been some problems in this feature. And these are kind of interesting because they're actually very similar bugs in two different implementations. There's the first bug, which was found in Firefox by their own internal fuzzing. And this was an issue where there was an integer overflow in growing this memory. So eventually you would grow the memory, and then it would think it was bigger than it was, and you could write out of bounds. And the second one, found by Zhao Kixun of Kihu, this is very similar, although it ends up being a use after free, where the memory is freed unexpectedly. Now, one thing I thought I would see a lot of, which I didn't see a lot of, was out-of-bounds issues. And I thought there was a few reasons for this. One is that there's actually a fairly limited set of instructions that can access memory in WebAssembly, pretty much load and store. So this is a very small and audible set of instructions that might go out of bounds. So right now, WebAssembly supports a very limited threading model. So there's not a lot of fear that you're going to check the size of something and then it's going to change. It also helps that memory buffers, you might notice, you can grow them, but they can never get any smaller. Once they're a certain size, they can only get bigger. But something else I thought was really cool is how they actually design these memory buffers on 64-bit platforms. It's called safe buffers or signal buffers, and it's actually quite cool. So what they'll do is they'll map the memory of 4 gigabytes for the memory buffer. And if you think about it, the way the instructions work, when you load and store, there's an unsigned integer offset. So it can go from 0 to FFFF, and that is 4 gigs in size total. So they have mapped all this memory that the index of a load or store instruction can actually access. And then the part that's actually allocated, they map to being read-write memory. And then when you run WebAssembly, if the memory is mapped, it works properly. And if the memory is not mapped, it throws a signal or an exception, depending on platform. And then this gets detected by JavaScript, and then they create a JavaScript exception. So I think this is cool, because it's very effective. You don't need manual bounds checks, and I think it's very unlikely you're going to have a bug where something larger than the size of an integer tries to access this memory. But I also like how it puts all the burden of the bounds checking onto people who go out of bounds. If you don't go out of bounds, this has no performance impact for bounds checking. It's only if you go out of bounds, then there's a lot of performance impact for creating that exception. And I think that's a pretty cool design, and I think it's one of the reasons that there's been very few out-of-bounds issues in WebAssembly. Though one problem with this is it doesn't work on 32-bit platforms. They have to use regular buffers there. But still on 64-bit platforms, I think it's fairly unlikely there'll be out-of-bounds issues, specifically in the memory. So like the memory, the other thing that gets imported is the table. And this is basically a table of functions, and they have to be WebAssembly functions. So if you want to call a JavaScript function from a table, you have to create a WebAssembly function that calls that function. And it's similar to the memory. You create one with initial size, and then you can grow it. And once again, there were kind of the similar bindings issues with these. The Firefox issue also occurred with tables where there was the integer wrapping. And then there was this issue submitted to the Chromium Rewards program where when you grew a table, like all things in JavaScript, if there's an index, you have to convert the index by calling toInteger, and then that can make calls that change the property of the table. And this ended up being, once again, a use after free, similar to the memory one. So what happens after you've loaded the imports? Well, now you get to initialization. And this is basically when you have an option in the section to initialize both your memory and your tables. So data segments are used to initialize memory, and element sections are used to implement the table. And I thought there were a few possible bugs here. One thing I thought is, this is going to go out of bounds like somewhere on some platform, but I checked the implementations on all 4 browsers, and I didn't see any issues like this. And I think one of the things that led to that is this is very well specified. There are very specific checks that are supposed to be made, and they were all consistent on all the platforms. However, there was this one fairly interesting issue in V8. And it kind of came up twice, and I don't have a CVE for it because the Chrome team actually found it before I found it. So here's what the issue was. If you think about how tables work, there is an instruction call indirect that you can use in WebAssembly that will call into a table. And then that table can call into JavaScript. And then that JavaScript can change the table. So the original issue was if that JavaScript changed the table to remove the function that it was calling right now, that would be the last handle to that function, and then that function would go away, and that would be a use after free. So they fixed this, at least for the short term, by detecting this situation. If you're already in a WASM call, you can't change a table. And this was actually okay. I forgot to mention, but tables are one of those things that you can do a lot more with them than is necessary in code. So any compiled code will only ever change their tables at startup. And there's pretty much no reasonable reason to change them dynamically during execution. But of course, it's still possible. So they just made it so that you can change them during execution, but not actually during a WASM call, which is fairly reasonable considering what compilers generate. But then I found another way to actually reach this issue, which is, let's say you do the same thing. You call the function but instead of removing it from the table directly, you load another WASM instance into the same compartment, and that one has initialization. Then that initialization will initialize the table, and then that will once again wipe out that last reference to the function. So now this has been fixed in a way that they just keep a reference to that function much longer than the table. So what happens now? Well, we've finished all the steps of loading our WebAssembly. We've created the module, we've created the instance with all the imports, and now we get exports back. And yay, finally, we can call these exports, and WebAssembly happens. So what happens next? Are there such thing as WebAssembly runtime issues? And the answer is yes, though I didn't find that many. And I guess there's a couple of reasons for this. One is that I think at every stage of WebAssembly, finding bugs becomes more difficult. And if you look at kind of the amounts that have been found, the parsing and module issues, there's a lot of them. And then there's kind of fewer instance issues. And then there's very little runtime issues. And I think it may be just because as people find bugs, you tend to go deeper and deeper each time. So it's possible there'll be some in the future. But also, I think the way that WebAssembly is specified and the limited number of features really does reduce the likelihood that these types of issues occur. So one possibility is that instructions do the wrong thing. And there actually have been a few issues like this, especially if you go through the bug tracker of WebAssembly implementations really early on. If you look at the first months or even before they actually put it into stable browser, there's a lot of issues like this that cause crashes, but a lot of them were removed by fuzzing before they were even released. There was incorrect bounds checking, and I discussed this earlier. I think because of safe buffers and signal buffers, this one will probably not come up except on 32 bits. And then incorrect handles and use after freeze. There's been a couple of these, though most of them seem to have been in loading and not in actual execution. So I think things are fairly good right now, but there are two future features of WebAssembly that I think will change the security landscape of it a lot if they go in. One is concurrency. Right now, there's not a lot of threading supported in WebAssembly. It's just JavaScript threading, but a lot of people want there to be threading within WebAssembly. And I think this will completely change the security properties of all the code that exists, and this will make it much more likely that there are bounds issues, that there are certain types of use after free issues, that sort of thing. And it will also make it a lot more difficult to write secure WebAssembly code itself. There's also WebAssembly GC, which will probably come in the future. And this is basically to solve the problem where you can't compile Java because cutting up that one slab of memory you're allowed to have is too performance intensive. So they think in the future there's going to be a way to request memory, a small piece, and use it in WebAssembly and then have it managed by the interpreter. And once again, I think this will make all the good things about how memory works right now a lot less certain, and I think there'll be more bounds issues and that sort of thing if this specific feature goes in. So to end off, I found several vulnerabilities in WebAssembly implementations, but funnily enough, I actually thought it was pretty good. There were definitely some implementations I didn't find any bugs in, and considering we're coming from a place of we want to run WebAssembly securely on the web, I found there weren't actually that many bugs compared to what I was expecting. And I think it's due to a few things. I think it's because WebAssembly has a limited number of features that are necessary. It's because the way they design the features, especially things like signal buffers, made it less likely for specific problems to occur. And all the features are very well specified, and it's very clear. So what will happen to WebAssembly in the future? I don't know. I think it's very possible, though, that it becomes the next Flash or JavaScript or Java. And I think whether it's secure in the future will depend on which of these features go in and how they're implemented. So I hope that WebAssembly does go the direction of security in the future. Thanks a lot.